So this is the 2019 Unit 1, 251 exam, version B. All right, leading off with a couple nomenclature questions. Cyclobutane, 1,1-dimethyl. Might as well give them the lowest number possible. That's why it's 1,1 on the carbon there. Naming, find the parent chain. Parent chain here is octanol, 1-octanol, so it's on the 1 carbon. So you draw the whole octanol chain, and then from here you just fill in what it is. So 3-ethyl, ethyl, 2 carbons, 4-methyl, 1 carbon, 8-chloro. So if you're given the name, usually if you're given the name, it's a little easier than given the structure. This one, again, you're trying to find the longest parent chain name here. So this is an amine. So this is going to be an amine. So 1, 2, 3, 4, 5. So the nitrogen is long off a pentamine, and it's off the 1, 2, 3 carbon. So we say 3-pentamine. And the other thing off this nitrogen is an isopropyl, which is one of those groups I wanted you to know. So it should be N-isopropyl 3-pentane amine. You know, notice a couple with isopropyl, one with propyl, right? Versus isopropyl. These are the wrong numbers. The nitrogen is off the carbon number 3 of the longest parent chain with the nitrogen. So kind of be on the lookout for those kind of things. Circle the correct wedge and hat structure for the thing below. Again, seeing this, you should recognize the bromine and the OH are on the same side. The ethyl is on the opposite side. So you want to find things with bromine and the OH on the same side. And that doesn't narrow much down. That's a methyl though, so that wouldn't work. And if I numbered my carbons, that should probably really help. So bromine needs to be 1, right? So bromine's 1, 2, 3, 4, right? See, this relationship's not right. And this other one here, the bromine's next to the ethyl, and here it's not. So this one's really about different places on the ring is that. So number your carbons would really help. Pretty challenging question, but number your carbons would really help you see this. And obviously, paying attention that that's a methyl, not an ethyl, would also be important. All right. How many hydrogens in the molecule, right? This is just being able to recognize where the hydrogens are at. The tough one here is probably, people miss that H. It's there. Answer is 12. Being able to recognize these are 3 CH3s, so that's 9, 10, 11, 12. Right? There's no hydrogen here because this carbon right has 4 bonds. No hydrogen here, that carbon has 4 bonds, there or there. Right? So recognizing those things again, how many hydrogens are in this molecule. What type of orbital overlap is responsible for the sigma bond between the carbon and oxygen? So again, questions we've worked on. So sigma bond between the carbon and the oxygen. So this oxygen is sp2 hybridized. This is sp. So the sigma bond is going to be from an sp2 orbital and an sp hybrid orbital. So it would be C. Of course, it's not P. That's nothing to do with p orbitals because p orbitals make pi bonds. So it's not that. It can't be anything with sp3. And this is an sp3 hybridized. So really, again, identifying hybrid state for each of these, and then what are the hybrid orbitals that go with that state, and knowing those things. Yeah, I'd be remiss to forget, right? So this carbon, this is called an isocyanate, actually. Use this in my research somewhat. But this carbon, because it has 2 pi bonds, right? Because it has 2 pi bonds, right? It's sp hybridized. It looks a little different than you're used to, right? You're used to seeing it right like this, right? This carbon has 2 pi bonds, right? But this carbon has 2 pi bonds too. It's just 1 pi bond to the oxygen and 1 pi bond to the nitrogen. Still sp hybridized though. So that's why it has that sp hybrid orbital. So this is one of those practicing using reaction arrows, curved arrows, where you're given the starting material, you're given a product, and it says basically draw the arrows to show the bonds breaking and bonds forming. First, once you add in all the lone pairs in the product below, so you assume everything is a full octet. So you add in all the lone pairs to there, 1 there, 1 there, plus charge there, and 1 lone pair there. So you assume everything is full octets, so you fill in and add your charges. Then you want to draw curved arrows to show the electron flow in the reaction below. So those are mechanism arrows again. So if you see this OH, you need to make an OH bond. And it looks like you need to make a pi bond as well. And it looks like you need a break, right? This carbon here has three H's on it, and here it only has 2. Right? Here it only has 2. So that's the other bond. Yeah, you need to break or lose a CH bond over here. So this oxygen takes that H. That's forming this new bond. The 2 electrons in the sigma bond between carbon and hydrogen break, and they go between there to form that new pi bond. And you have the plus charge now is on the oxygen. This is one that lost electrons, right? It's one that's donated electrons. And that's what you want to do it. And then it asks for specific atoms on the left as nucleophile or electrophile. Again, nucleophile is electron rich, so that's the oxygen. That's where your arrows start. Where your arrows end up at is that hydrogen. So that's considered the electrophile. It's electron deficient. And that's where those things would be at. All right, Newman projections. So I say draw the exact conformation of Newman projection as shown in A below from the wedge and hatch structure. So assume I'm telling you to look from 1 to 2. Right? If you see 1 and 2, assume this is the Newman projection I want you to draw where you're standing here. I mean, if you don't, it's fine. Little hat, right? Make sure you're looking down 1 to 2. So again, if you're looking at this, make your Newman projection. OH is at my feet, SH is at my head, so this is in a staggered conformation. So hopefully you can translate that onto your Newman projection. OH, SH. On your right hand would be an H. That ends up on your right over here, H. H and OH are both wedged, so they're both on the same side. On your left hand is this tert butyl, so that's on your left here. The tert butyl and the H are both on the same side. Now here you gotta be careful with directions. I say, I could say clockwise. I could say carbon 2. I could say counterclockwise, right? Make sure you read these directions very carefully. Right? I'm not going to give you the exact same question. So you rotate carbon 1, so that means the back just stays the same the whole time. Right? And all these, you can just keep the back the same. And all you're going to do is rotate each of these. The tert butyl will be on top there. H goes there. So now it goes from staggered to eclipsed. Rotate clockwise again. Again, the back just stays the same. Just draw it in as it is. Rotate it. Now went from eclipsed to staggered. Rotate it again. Now we're back to eclipsed. That's what we're looking for that. And then, which has the highest energy? Explain your reasoning. So obviously it's going to be the ones that are eclipsed. So that would be B or D, one of those two. And then you want to look for the biggest groups on top of each other. I think I would say, I said D. Yes, D, because in D, you have the tert butyl and the OH on top, and the OH and the SH, whereas here you have the H's on top of the OH and OH. So this is a little bit worse, a little higher energy. So we want these eclipsed things, and the biggest groups are the tert butyl and the SH. Sulfur's bigger than oxygen, right? So that's another reason why. So for sure eclipsed, and then those big larger groups. Atoms. Don't call them molecules. They're atoms. They're not molecules themselves. Atoms on top of each other. Match reactions, addition, substitution, elimination, rearrangement. 2 points each. If you add something, right, you're adding something, that's an addition reaction. Right? Usually adding across a pi bond. So here you added a nitrogen and a hydrogen. Let's see, here you had an I and you exchanged it for this. Oops, I lost a carbon there. My fault. Right, so this would be a substitution reaction. Here, you know what happened? You formed a pi bond, right? So that has to be an elimination reaction. Elimination reactions form pi bonds. Essentially, what's left, right? Did you get some sort of weird? This is a rearrangement where this carbon actually ends up. Oh golly. Up. Oh, I think this is a Curtius or a Beckmann rearrangement. Anyway. The molecules move, right? Their rearrangement in space changes. So that's called rearrangement. All right. Draw the mechanism arrows. So that's like reaction arrows, curved arrows, on the starting materials to form the products. Right? So what bonds are formed, what bonds are broken. So it looks like we formed a new OH bond, and we broke an OH bond. So we need to show arrows to show that. Start our arrows at electron density, the nucleophile. Electrons go there, grab the hydrogen, forms that bond. Same time this OH bond breaks, those electrons go there. I'm going to do the negative charge there now. And then the question is, will the starting materials or products you favor this equilibrium reaction? Briefly explain your reasoning. So this is asking you to think about those 5 factors that affect acidity. So in this case, the factor is going to be induction. So you're looking at fluorine versus bromine. And one's more electronegative than the other. Fluorine is more electronegative than bromine. It pulls more electrons, right? It's not about size here. So the starting material is going to be more favored because the fluorine is pulling electrons. And that's actually going to stabilize this O minus. Another way you can think about it, if it's fluorine pulling electrons, it's making this H more delta plus because the electrons are being pulled, right? That's called induction. So you can look at it this way or this way. But that explains why the starting materials are favored. Because this is going to make, the fluorine is going to pull, make this more reactive, more delta plus. And also because this fluorine pulls, it makes this O minus more stable because it's helped pull the electrons away. So they're not willing to react. Using arrows, so these are resonance arrows, right? Just curved arrows, moving 2 electrons at a time. Draw 3 potential resonance structures for this molecule below. So again, here, keys are atoms don't change position. You're doing resonance, right? Atoms don't change position, don't break sigma bonds, only move lone pairs and pi bond electrons, right? And balance your charge. So this starts out with no charge. That doesn't mean when you draw a resonance structure, it can't have charge, but it needs to be neutral at the end. It needs to add up to 0. If you see a lone pair in the ring or outside the ring, right next to the ring, they're going to be able to donate electrons into these rings. So electrons go in, pi bond breaks, and electrons go to that carbon. It has a negative charge, it has a lone pair there. Nitrogen moved its lone pair, now it has a plus charge, right? Nitrogen with 4 bonds has a plus charge. These electrons can now go, right, make sure their spot they're going in between the bond, right? The placement's important. We practice that on Achieve. Electrons go there. This pi bond breaks. Electrons go to that carbon. Again, balancing our charge, plus charge, minus charge. Now we can push these electrons out towards this, right? Because this is an oxygen, it's pulling electrons, right? This carbon is delta plus. Move the electrons there, form a new pi bond, breaks the carbon-oxygen pi bond. Now the minus charge is out here in the oxygen, right? This is one way. You could do it. There's other ones you could do. This is just one possible way to do it. But make sure you have 3 of them, 1, 2, 3. Right? Balance your charges, have your arrows, all that good stuff. All right, hybridization state, nothing too challenging here, hopefully. No pi bonds on this carbon, sp3. This oxygen, no pi bonds, sp3. This carbon, 1 pi bond, sp2. Right? This carbon would be sp, but I'm pointing that arrow there, 1 pi bond, so it's sp2. Hopefully pretty straightforward at this point. Some of these RNS, this is some tricky ones out here. Here, again, you're starting here, and you're going 1 bond out at a time. So carbon, 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 carbon. Everybody's tied. So then you look at this carbon, you say, well, this carbon's bonded to a carbon, and a hydrogen. This carbon is bonded to a sulfur, a hydrogen, and a hydrogen. This carbon's bonded to 3 other carbons. This carbon's bonded to a carbon and 2 hydrogens. Right? So if you look at these, who has the highest priority? It's not about total. High card wins. So sulfur has a higher atomic number, so that's why this is number 1. Then you have carbon, carbon, tie, carbon. H, carbon, carbon. This now loses, so now this is 4. And then between these two, you finally get to the third element these carbons are attached to. It's carbon versus hydrogen. So this one wins, so this is 2, 3. Once you do the rankings, which you need to do for points, right? This is literally a 5-point question. The whole thing's 5 points. 4 points are for your rankings. 1 point is for your RS, right? So make sure you get those things done. Do the rankings as best you can. For this one, again, atomic number, threw a little bit of a curveball. Boron we maybe haven't seen, but if you have your periodic table, you know boron actually doesn't have a higher atomic number than oxygen. So oxygen is 1, H is 4, then carbon versus boron. Carbon has a higher atomic number than boron. You're off to the races then, and you do what you need to do. Let's practice this one time at least. Model this out. So we could say this is red, This is green, white, and blue. So you want to take your model kit, your two mirror images. You want to map this on, so the green's coming out, red's going away from you. The white should be to your left, blue should be to your right. If you get that one of your two models, you grab the green ball, you turn it towards yourself, and you say red, white, and blue. Red, white, and blue. All right? White and blue. And it looks to me that this would be R. So you have your model kits, you can use them, have them ready to go. If you need help checking out, I can certainly help you check to make sure you have them as mirror images, no problem. The pairs below, which will have a lower boiling point. So lower boiling point would be less polarizable in this case. Iodine's bigger. This is actually one of the questions we had from our workshop, I think. So again, answer is worth 1 point. The explanation is worth 2. This one will have a lower boiling point because it's more branched, less surface area, less London forces. So that's what we're looking at here for these things. So pretty straightforward. All right, chair time. Let's do some chairs. So start with this chair, and it says perform the ring flip for the molecule below, then use wedges and hatches to show the same molecule on the blank cyclohexane ring. So here you got to do the flip. So you got to take the feet, pull it up. Right. So this chair leans to the left. You need to draw the chair that leans to the right. It's all methyl, so you don't really need to worry too much about numbering, but you could. I would, I like to number, and again, the numbering doesn't matter. I'm just doing this for myself to keep track of. It's not nothing to do with naming. You could have numbered it the other way. You could have done anything you want to, as long as you're consistent. 1, this is axial up. So on a ring flip, it's going to be, this is equatorial up. On a ring flip, it's going to be axial up. This is axial up. On the ring flip, it's going to be equatorial up. Equatorial up. On the ring flip, axial up. Notice, no matter what, these are all on the same side pointed up, and these are all on the same side pointed up. So this is the ring you could draw. You could, if you wanted to do hatches, you could. That's the same. It's fine. I always like to think, like I've said before, when I think of the up on the ring, I think of wedges. But that's just me. It doesn't have to be that way. We didn't talk too much about naming these kind of things. These are all cis, so you call it cis. 1, 2, 3 trimethyl cyclohexane. I also asked to circle the most stable chair conformation. Again, why is this one the most stable? This one has 2 axials, right? This one only has 1. Everything else is equatorial, right? Things being equatorial, bonds get away from each other, atoms get away from each other. That's always lower in energy. So that's why this one's the more stable conformation. Finally, for number 12, circle the elements that have 1,3 diaxial interactions. That's just a fancy way of saying, if you're looking at bromine, who else is axial on the same side? So I say this bromine is up. What else is axial up? The H and the fluorine. So just want to take a look at 12 again. And really what this is, what I want you to be able to do is recognize, if I say, here's the bromine, do you recognize what else is on the same side as bromine? Right? So what else is on the same side as bromine? This CH3, the chlorine, and that H. And then these SF and this H are both axial. Right? They're going to have the diaxial interactions because they're axial on the same side. What would be trans to the bromine? Right? Anything on the opposite side. I see this bromine pointed up, so the OH is trans. This H is equatorial down. This iodine is axial down. This H is equatorial down. This H is axial down. Right? Those are all trans to the bromine, right? So looking at something and knowing if it's the other things are on the other atoms are on the same side of the ring, or if they're on the opposite side. That's what I want you to be able to do from this.